As we all know, Arctic has been going through drastic climate change, and probably the most obvious climate change identification of the climate change was the loss of sea ice in the Arctic Ocean. And sea ice is only one component of the freshwater budget of the Arctic Ocean. It is often called solid freshwater component. Today I'm going to talk more about liquid freshwater. Freshwater is an essential climate variable in the Arctic Ocean and North Atlantic. It is directly or indirectly involved in the most of the feedback mechanisms. And some of the components of the Arctic Ocean climate system are listed here in this slide. And of course, I'm missing more than this. And there is very complex interaction of feedback mechanisms among all these components. But as you can see, the freshwater plays a crucial role in all this process, regulating the feedback mechanisms and through these feedback mechanisms, controlling the state of the Arctic climate. So shown here are physical mechanisms, but of course these physical mechanisms change the environment, so they impact the ecosystem. I'm not a biologist, but I try to somehow connect the physical mechanism with ecosystem. One of the most prominent impact of the freshwater is change of the optical properties of the upper ocean and sea ice. So sea ice melts, more light is available for the mixed layer, and so on. So the light levels in the ocean mixed layer increases, and this enhances primary productivity. And there have been many publications about this and this going on changes in the Arctic Ocean over the last several years. Several publications by Kevin Arrigo, for example, he clearly demonstrated the productivity in the Arctic Ocean has been increasing over the last 10 or 15 years. Today I'm going to talk more about physical process, but keep in mind that they're closely related to the ecosystem. So all the changes that I'm going to talk about today, they are going to impact the ecosystem in the Arctic Ocean. This is the study area with some geographic names that I will be referring to in my presentation. Here is a schematic diagram of the large-scale circulation in the Arctic Ocean and North Atlantic. So we have a transpolar drift, which brings the water from the Canadian basin to the Eurasian basin, and then through the Fram Strait to the North Atlantic. There is incoming North Atlantic water, North Atlantic current, where it splits into two branches to the Barents Sea, and one goes through Fram Strait into the Arctic Ocean. And there is one more important feature, the Beaufort Gyre. I'm going to talk about this a lot today. This feature is related to the anticyclonic gyre, Beaufort Gyre, which accumulates fresh water, both solid and liquid, in the Canada basin. These are the transects of the salinity and temperature, which are derived from climatology, GDEM4, and the transect goes from Alaska to the Kara Sea. And in the upper right picture, you see salinity cross-section. And you can see that there is about 200-300 meters of very fresh water accumulated in the Arctic Ocean, and this freshwater layer is deeper in the Canada basin. The bottom picture shows the temperature, which clearly illustrates the positioning of the Atlantic layer, very relatively warm layer in the Arctic Ocean, with a cold temperature in the Eurasian basin around 2, 3, or even 4 degrees, depending on the location. As I said, the Beaufort Gyre, which is located in this roughly in the center of the Beaufort Sea, is characterized by increased amount of freshwater content due to the convergent surface current, surface flow in the anticyclonic gyre. And here is another interesting feature of the subpolar North Atlantic, the convection side. So this cross section shows the density fields. Actually, it is temperature fields, and the isolines show the sigma layers, so it's densities. across the central Greenland Sea. And you see that isopycnus is dominant in the center of the Greenland Sea. That's where the deep convection is going on. And the domain of this isopycnus is driven by the cyclonic gyres, which is in their turn are driven by cyclonic winds dominant in this area. And the domain is very crucial because it preconditions the water column for the deep convection. Without this domain, the deep convection probably wouldn't happen. So Arctic Ocean is often compared with an estuary of the North Atlantic. Of course, there is a lot of idealization in this comparison, but it emphasizes the fact that the Arctic Ocean is greatly influenced by river runoff. There are other freshwater fluxes which are listed in this slide. These are net precipitation and Bering Strait inflow and net ice melt. There are two major routes of freshwater outflow from the Arctic Ocean to the North Atlantic. One is through the Canadian Arctic Archipelago and through the Fram Strait. Listed numbers are long-term mean estimates of the liquid and solid freshwater fluxes through these passages. And of course, there is a strong interannual and interdecadal variability of these fluxes from the Arctic Ocean to the North Atlantic. From time to time, on average every 10-15 years in the 20th century, the Arctic Ocean released a large amount of fresh water, and it is believed that this release of fresh water was linked to the generation of great salinity anomalies in the North Atlantic, which was observed in 1970s, 80s, and 1990s. The variability of the Arctic climate is often described in terms of the climate indices, and you are familiar probably with NAO and Arctic Oscillation Index. There is another one, Arctic Ocean Oscillation Index. Don't confuse it with the Arctic Oscillation, AO. This is a different index, although they're all correlated because they describe pretty much the same phenomenon, but use different methods to calculate the index. The AOO, Arctic Ocean Oscillation Index, the one that I'm presenting right now, is based on the sea surface height anomaly in the Beaufort Gyre. There are two climate states in the Arctic Ocean: anticyclonic and cyclonic circulation regimes. During the anticyclonic circulation regime, when the Arctic is dominated by strong anticyclone, the anticyclonic rotation over the surface fields is strong, which leads to the accumulation of freshwater and sea ice in the Beaufort Gyre. And the sea surface height anomaly increases. That's why it results in the higher AOO index. And the time series, which is over here, you see the quasi-decadal variability of this Arctic Ocean Oscillation Index during the second half of the 20th century. And this variability, this quasi-regular, quasi-decadal variability was interesting, and it was described in terms of these feedback mechanisms suggested in several of our papers. And of course, it is a conceptual mechanism, but however, this mechanism was reproduced in a simple box-based model, which is schematically shown on the left side of the slide. The important feature is that in this mechanism, the Arctic climate variability was controlled by the freshwater flux from the Arctic Ocean to the subpolar North Atlantic, and by the meridional atmospheric heat flux from the North Atlantic to the Arctic Ocean. The intensity of these fluxes determined the climate state in the Arctic Ocean and the North Atlantic. However, something changed in the system, and in the 21st century, we don't see quasi-decadal variability of the Arctic Ocean Oscillation Index. As you can see in this time series, the Arctic Ocean has been dominated by the anticyclonic regime during the 21st century, which is more obvious in the wavelet analysis. You see there is a quasi-decadal, very strong quasi-decadal signal in the 20th century, but it is absent in the 21st century. So the question is, what has happened with the Arctic climate system? What caused the cessation of the quasi-decadal variability in the Arctic Ocean North Atlantic climate system? So we were puzzled by this observation, And we thought that there is something going on in terms of freshwater redistribution and freshwater fluxes that we were missing in our conceptual mechanism suggested for the 20th century variability of the Arctic climate. So let's look what has changed in the freshwater budget in the Arctic Ocean in the 21st century. So this slide summarizes the most notable changes in the freshwater budget and freshwater fluxes. And as you can see, all components of the freshwater budget have been increasing except for the multi-year ice. As you know, the multi-year ice has been decreasing in the Arctic Ocean in the 21st century. And this results in the noticeable net ice melt. So the multi-year ice was melting and was replaced by seasonal ice, but the excess freshwater, solid freshwater, became net liquid freshwater. So that's why we have positive net ice melt, plus 8%. So all the fluxes are increasing, and overall the Arctic Ocean freshwater budget has been increasing in the 21st century. Where does this freshwater go? It, according to the observations in Fram Strait and Canada Arctic Archipelago channels, the freshwater transfer from the Arctic Ocean to the North Atlantic hasn't changed a lot during the 21st century, which tells us that most of this freshwater is still in the Arctic Ocean. It is in the Beaufort Gyre, most of it. So with all this in mind, we decided that there must be some other freshwater source of freshwater that we have been missing. And it turns out that it could be Greenland. So we know that Greenland has been melting, accelerating the melt during the 21st century, and it's probably this excess freshwater flux that we neglected in our hypothetical conceptual mechanism. So the black arrows indicated the mechanism that I showed before, but you see that there is another source of freshwater that we neglected, the Greenland freshwater flux. So this freshwater flux is advected into the subpolar North Atlantic. It changes the thermohaline process, it changes convection, and it interacts with the feedback mechanism which I described earlier. And these are research questions that we are trying to answer at the moment, because this hypothesis, we need to validate it. We need to be able to show, to prove that Greenland freshwater flux can impact thermohaline changes, and through this, the climate variability in the Arctic climate system. This slide shows Greenland freshwater flux. It changes how it changes in the 20th and 21st century. These figures are courtesy to Jonathan Bamber. And during the 21st century, as I said, the Greenland has been melting, and the melt rate has been accelerating since 1990s. By now, according to Jonathan Bamber, the volume of the surplus freshwater flux has achieved about 6,500 cubic kilometers, which is roughly half of the 1970s Great Salinity anomaly, which tells us that potentially it can influence thermohaline process in the North Atlantic. It is not quite yet the Great Salinity anomaly in terms of the volume of fresh water, but it is approaching it, and probably in another 10 or 20 years it will be around 10,000 cubic kilometers, which is a substantial amount of fresh water. What we don't know is the accumulation rate of this fresh water, how long it stays in the subpolar North Atlantic. Or does it stay there, or is it flushed away to the tropical regions? So this kind of questions we're trying to answer. And in order to tackle these questions, we organized coordinated modeling experiments within the FAMOS, which stands for Forum for Arctic Modeling and Observational Synthesis. This program is funded by the NSF, and I think that this work has been very successful within FAMOS because we already completed the first phase, we published the paper, and now we are in the second phase of this work. So there are several modeling groups which track the propagation of different freshwater in the Arctic Ocean and the North Atlantic. And specifically, we are looking at the Greenland freshwater propagation. So today I'm going to talk about only one model, the one that I ran. This is the coupled 0.08 degree Arctic Ocean high-camp sea ice model. This gives us a resolution about 4.5 kilometers in the Arctic Ocean and about 7 kilometers in the North Atlantic. So here is high-camp domain, here is vertical grid. The vertical grid is hybrid, so it includes isopycnals, Z level and sigma levels. And on the right, this is the Greenland freshwater sources. So we are using very detailed information about freshwater sources in the along the Greenland coast provided by Jonathan Bamber. At every of this point, I release passive tracers. Besides Greenland, I also release passive tracers at different locations around Arctic Ocean coast, Mackenzie River, Pacific Water, west and east Eurasian rivers. Now we're going to see an animation which shows the propagation of the Greenland passive tracer, which tracks the Greenland freshwater. So the colors indicate tracer concentration. Note that this is logarithmic scale. Red colors show very high concentration, and the purple and blue very low concentration. So what we see here that the tracer tends to propagate with the boundary currents with the East Greenland current, with the Labrador current, then it goes into the subpolar gyre, and then with the North Atlantic current, it goes into the Nordic seas, where it mixes into the interior Greenland Sea and the Iceland Sea. So what is important here, this is of course qualitative results. We do have quantitative analysis, but here what is important to see is that the tracer tend to accumulate in the Labrador Sea, in the subpolar gyre, and they do propagate spread into the convective sites, which are here, the Irminger Sea, here, and the Labrador Sea. So do we see any evidence in observations that show that the Greenland freshwater can accumulate in these areas that I showed in the animation? So in order to look at this, I calculated the freshwater content from global high-camp encoder reanalysis. This is not truly observational product, but it does assimilate observations. So I calculate freshwater content for these boxed regions, and we see there is a drastic increase of freshwater content in the Labrador Sea in the 2010-2015, in the subpolar gyre, and the Irminger Sea. Of course, I cannot say this is necessarily Greenland freshwater, but it does agree with the results that I showed in the animation. So potentially it could be. Now we're going to see the animation for the other freshwater tracers. So colors again show the tracer concentration. So this Mackenzie River, this is Eurasian River East, Eurasian River West, and this is Pacific water. What is interesting is that all freshwater sources have very different pathways, and simulation, the models do allow us to track each freshwater source individually. You see how different their pathways, and what we see in the animations is that the Eurasian River do not spread into the Beaufort Sea, and the Beaufort Sea is largely dominated by the Mackenzie River and the Pacific water. This is the summary of the animation that I just showed to you. So what is intriguing is that it seems that the Eurasian basin and the Canada basin can be sometimes isolated. And I found that the same conclusion in other model results. For example, Mikhail Karcher published his results in 2012, where he looked at the propagation of the iodine in the Arctic Ocean. And he also noticed that in some years, the tracers from the Eurasian basin didn't spread into the Canada basin, and the Arctic Ocean was kind of partitioned into separate domains. Okay. Another interesting feature is the very narrow band of the Eurasian water, which is advected from the Eurasian shelf into the North Atlantic. And this is due to the transpolar drift in this figure, which shows the annual mean ocean surface circulation. From the model, you see there is very obvious transpolar drift, which pulls the water from the Eurasian shelf directly to the North Atlantic. And in the Canada Basin, we have anticyclonic circulation, whereas in the Canadian Basin, it is more like cyclonic circulation. And between these two cells, we have the accelerated transpolar drift, which very effectively transfers water from the Eurasian Shelf to the North Atlantic. This time series shows the evolution of the fresh water from different sources in the Beaufort Gyre. What is interesting is different time, spin-up time for the Mackenzie River and the Pacific River. It takes for the tracers about 6 to 7 years to level up in the Beaufort Gyre, whereas for the Eurasian rivers it takes about 15 years even to show their presence in the Beaufort Gyre. Another interesting feature is 2012, when there is a very drastic increase of the amount of Eurasian waters in the Canada Basin. And the year 2012 was a cyclonic year. It is the year when the Beaufort Gyre was relatively weak, and this probably allowed the fresh water from the Eurasian Shelf to spread into the Canada Basin. So schematically what happened during the anticyclonic regime, we have this position of the transpolar drift, which pulls all the water from the Eurasian Shelf into the North Atlantic, whereas during cyclonic regime 2012, the transpolar drift shifted more towards the Bering Strait, and this allowed the Eurasian river water spread into the Canada Basin. And this is the evidence from the model 2012. You see the very weak Beaufort Gyre, and the transpolar drift is more oriented in this position. Also, there are changes in the circulation on the Eurasian Shelf. And during the anticyclonic year 2013, strong anticyclonic Beaufort Gyre with very strong transpolar drift over here. And at the end, there is another interesting animation which now shows how the fresh water from the Beaufort Gyre spreads out of the anticyclonic gyre. So I seeded Lagrangian particles. So each particle represents some amount of fresh water in the Beaufort Gyre. And the background color is salinity from the model. So the dark blue shows low salinity and the yellow high salinity waters. So you see during the first several years, some of the fresh water escaped into the Labrador Sea through the Canadian archipelago, but still the majority of fresh water is still in the Beaufort Gyre. And remember that anticyclonic gyre has a convergent flow in the upper ocean. That's why the particles tend to stay in the Beaufort Gyre. Nevertheless, through the time, part of the fresh water is escaped into the North Atlantic. Now we see part of this is going through the Fram Strait into the North Atlantic. Okay, so with this I'm going to wrap up. The summary of my presentation was that I tried to show that the fresh water is the key component of the Arctic Ocean North Atlantic climate system. It is directly involved into the feedback mechanisms and the distribution and the freshwater fluxes between the Arctic Ocean and the North Atlantic regulate the Arctic climate variability. So we have two experiments, two sets of the experiments with Greenland freshwater tracers and Arctic Ocean freshwater tracers. And they do show that the pathways of the freshwater is different. The freshwater can spread into the convective sites, both from Greenland and from the Arctic Ocean. And this is important because convective sites are cyclonic, which have divergent upper ocean circulation. And in theory, no freshwater shouldn't spread into the convective sites. But the model does indicate that the freshwater propagate into the convective sites, which means that potentially it can influence thermohaline circulation and convective activity there. So, and what is in the future? Well, keeping in mind that the amount of fresh water accumulated in the Beaufort Gyre is around 6,000 cubic kilometers, and given the fact that the Greenland freshwater flux, surplus freshwater flux, integrated over the 20-something years is also about 6,000 cubic kilometers. If all this fresh water ends up in the North Atlantic, we probably will have slightly different climate. All right, thank you for your attention, and I'm open for questions.
Thank you very much, Dmitry. There is already one question here in the room, Dr. Shen Li.
Yeah, I'm just curious about your freshwater tracer, how you define them. Is it based on particular salinity threshold?
how do I define what?
You have a fresh water, you trace them, along our different river input. So you trace that as a particle or as like defined as a oscillatory.
Well, the model allows to add so-called passive tracers. So it's like another tracer. So you have temperature, you have salinity, and you have passive tracer. So you add some concentration at specified locations, and the model uses the same equations to advect it, to mix it with the ambient water. Then these tracers, they're called passive because they are not involved in dynamics at all. So they do not impact the dynamics. The dynamics impact their advection and their mixing, but there is no back influence on the dynamics. Like, for example, temperature and salinity, they change the density, right? And density change the dynamics. So the passive tracers do not impact the dynamics. Okay, so you can think about this as a dye. So you put a dye of different color in the specified locations, and the amount of dye or concentration of dye is proportional to the amount of fresh water released at this location.
Okay, thank you.
Okay.
Any other questions for Dmitry? I have one question or two. Some of us involved with IRPIC are, or has been for a while, interested in conceptualizations, especially panarctic conceptualizations. And your presentation seems to be very relevant to the riverine coastal domain, or RCD, that was published last year or a couple of years ago by Eddie Carmack. It will be really interesting to see, more than interesting, it will be important to advance on the dynamics and the variability of the RCD as conditions change, and see how it responds to atmospheric, especially atmospheric forcing. Have you thought about that, or do you have any plans to work on that?
Yes, our work is directly related to this very interesting problem, the RCD and the dynamics of the river plumes. Until now, most of the models were limited by their resolutions because the river plume, the spatial scale of the river plume is relatively small in terms of the Rossby radius of deformation, which is in the order of only a few kilometers or even maybe less than that. According to Sheldon's paper, it's on some of the shelves, and during summer and spring season, it could be less than a kilometer. But let's say it's in the order of 2-4 kilometers. Most of the Arctic Ocean models do not resolve this kind of scales. So now we start approaching to resolve the scales. With this model that I showed, the resolution in the Arctic is around 4 kilometers. We're still not probably there yet, but I think we're close. So we can simulate dynamics more or less accurately, I think. We have another configuration, which is 2 kilometer resolution Arctic Ocean model, and this model should be able to capture most of the river plume dynamics correctly. Yes.
Yeah, my question goes beyond river plumes. Actually, the RCD is, on average, typically is 15 kilometers wide, and it goes all around the Arctic Ocean.
Yeah.
And it acts as a connector between the terrestrial and the marine domains. So I think I can send you the paper, but I think it's something that your model could probably replicate and provide some useful information on its variability on which we know very little or almost nothing, because the only paper or one of the only papers, it's basically a conceptualization. It's there is no associated variability in the original paper by Eddie Carmack.
Yeah,
yeah.
Go ahead.
Yeah, go ahead, sorry.
Well, I briefly looked through this paper. It is a very interesting paper. And obviously our model, the one that I showed today, is capable to capture the zone, the RCD zone. Yeah, because the resolution is 4 kilometers, so we'll have at least 4 or 5 points within this RCD zone. And if we go back to the animation that I showed, I think we do see this dynamics which is described in this paper. For example, sorry, let's look at this lower left movie, which shows the propagation of the West Eurasian rivers. You see the river flow, which is shown with tracers, which pretty much the river water is trapped right near the coast, and that's what Eddie Carmack is talking about. And then it mixes over here. Yeah, and then it mixes up. So I don't know about this whole idea. I saw one of his pictures show that this RCD region goes all the way through the Bering Strait into the Northern Pacific Ocean. Yeah, we can look at this more in the model. It wasn't the focus of this study, but I do see some of the some regions that do show similar dynamics, which is described in Eddie Carmack, or some similar features. So, for example, East Greenland current, the fresh water is very trapped. There is almost no escape of fresh water into the interior Nordic seas within the East Greenland current. Same as here in the Barents Sea. But over here, I see a lot of mixing going on. So, yeah, we'll see.
Thank you. Are there any other questions for Dmitry?
Hi, Dmitry. This is Renu Joseph. I called in a little late, but one very, very general question that I have is, it is great that you have these tracers and you can see how the stuff flows, but I was also wondering, do we have observations or metrics that we can use to evaluate from a general perspective how well the models are performing? And if so, what are they? Can you talk a little bit about that?
Yeah, this is a great question, Renu. Actually, this is what we are trying to solve right now, because we have pretty good agreement among the models, but we need observations. And we have been in contact with a Canadian group, GeoTraces. If you know this program, it was funded by the Canadian government, I think by the NSF, and some other agencies, which I don't remember. But it was largely Canadian and US participation. And this study collected observations of different geotraces in the Arctic Ocean. And I presented my results in the workshop in May in Vancouver. And we found a lot of similar results. And what we were talking about is that, look, we are doing the same thing, but you are doing with the model, and they're doing this with geotraces. So we are trying to connect our two studies somehow. It is not always easy because, for example, my understanding is that geotraces cannot necessarily tell us how much of fresh water from Eurasian basin came to the Beaufort Gyre, or when did it come, which is important for validating our model. But at least it can definitely, this observation can help us to do at least sanity check, saying that our model at least makes sense. Yes, yeah, we're working on this.